Now let's turn our attention to one-dimensional kinematics problems, motion problems. I like this far side. Okay, now listen up. Nobody gets in here without answering the following question. A train leaves Philadelphia at 1. You're traveling 65 miles an hour. Another train leaves Denver at 4. Say, do you need some paper? My wife is one of the most brilliant people I know, and yet in high school this was her greatest fear. Now I had fears in high school. I was afraid that the big guys were going to put my head in the toilet and things like that, but I wasn't afraid of these. Now, once you see how to solve these problems, you'll never be afraid of them again. They are so easy. Let's start with a simple one. A car has an initial velocity of 30 miles an hour. It accelerates at 2 miles an hour each second for 10 seconds. What is its final velocity? You can do this in your head, people. Talk to your neighbor. Okay, what's the answer? Yeah, it's 50. Okay, what you did is you took the initial velocity of 30 miles per hour, and during the first second, you added 2 miles per hour. And then during the second second, you added 2 miles per hour. And then during the third second, you added 2 miles per hour. Now, when you find yourself adding the same thing over and over and over again, we got a clever way to do that. It's called multiplication. Okay? We add 2 miles per hour for each second, and we do it 10 times. Now, that's what gave us the 50 miles per hour. We started with 30 and we added 20. Now, in terms of variables, this would be my initial velocity, this would be my final velocity, this would be my acceleration, and that would be my time. And that's the first of our kinematic equations. Now, this is not the first time you've seen this. It's just the first time you've seen it in this form. Let me show you. If I subtract V initial from both sides, this becomes V final minus V initial is equal to A delta T. Final minus initial is delta V. If I divide both sides by delta T, this just becomes A is equal to delta V over delta T. And that's the operational definition of acceleration. I should put 3 lines here. Okay, so this first kinematic equation is just a rewrite of our operational definition of acceleration. Let's try a harder problem. A child slides down a constant slope on a toboggan. Folks, the most important words in this problem are constant slope. These kinematic equations that I'm teaching you are only valid when there's constant acceleration. They've got yellow caution tape around them. Don't ever dream of using these equations unless you have constant acceleration. Fortunately, those are the problems that we're going to be solving in this class. Okay? Now, the fact that this toboggan hill has constant slope, as you learned in tutorial, that means it has constant acceleration. So we can use these equations. When the child passes her older brother, he estimates she's going 2 meters per second. When she passes her younger brother 10 seconds later, he estimates she's going at a speed of 10 meters per second. About how far apart are the two brothers standing? Talk to your neighbor. Okay. Let me remind you that when you're trying to calculate how far you're going to get on a road trip during the day, you don't want to use the fastest speed, you don't want to use the slowest speed, you want to use the average speed. So what's her average speed during those 10 seconds? Her slowest was 2, her fastest was 10, and we've got uniform acceleration in between. When we have uniform acceleration between, we can find the average by doing this. The V average is just equal to V initial plus V final over 2. Or I could write that as 1/2 V initial plus V final. So I take the slowest of 2, add it to the fastest of 10, that gives me 12, divide by 2 is 6. On average, this young lady was going 6 meters each second down the hill. And she did that for 10 seconds. How far are the brothers apart? 60 meters. 60 meters. Now, what we used was the operational definition of average velocity. It was just the total distance divided by the total time. Now, I could rewrite that as delta x is equal to V average delta t. But V average, remember, is just halfway between the slowest and the fastest if we have constant acceleration. So I can rewrite this as delta x is equal to, I'm going to use a different color here. That's my V average. That's this thing here, times the time. And that, my friends, is the second kinematic equation. Now I want to emphasize that these are just shortcuts for things we already know. We could already solve these problems just using the operational definition of acceleration or the operational definition of average velocity. These are just more convenient. Now, with these two equations, we're ready to solve this problem that we presented last week. You remember we have this ramp that's 2 meters long. We start the cart at rest, and we let go, and it speeds up. 1 1,000, 2 1,000, 3 1,000, exactly 3 seconds to get down the ramp. Now that gave us an average velocity of 2/3 meters per second, or 0.67 meters per second. Now, the question was, if this cart had a speedometer magically in its side, that speedometer would start at 0 and get a bigger reading as it went down. At some point, the reading on that speedometer would be 0.67 meters per second. At that location, the average velocity and the instantaneous velocity would have the same value. And we asked, where does that happen? In the middle of the ramp, the upper half of the ramp, or the lower half of the ramp? Do you remember what the correct answer was? The upper half. But some of you are scratching your head and saying, why? Well, let's see if we can understand. If I start with 0 velocity, and I have to have an average for the whole trip of 0.67 meters per second, exactly twice the average, okay? It's got to be twice the average. Now, if you can't see that, let me help you with an analogy. Suppose you get a job selling shoes, and the owner says, look, I'm going to give you a trial of 2 weeks. If you don't sell 5 shoes a week, on average, you're out of here. You are fired. Oh, and I'm going on vacation for 2 weeks. I'll see you in 2 weeks. So the first week goes by, and you sell no shoes. You're not good at this. Okay? Nothing. So, how many shoes you got to sell the second week in order to not get fired? 10. Because your average has got to be 5, and you got 0 to start with. Okay? So, that's what's going on here. If I take this plus this and divide by 2, I better get the average. Now, the question is, if this speedometer goes from 0 up to twice the average, where does it get to 1 times the average? Is it going to be halfway in distance or halfway in time? And the answer is halfway in time. If we look at this velocity versus time graph, we recognize constant acceleration by the straight line. That means that every second that ticks by on your Mickey, you increase your velocity by the same amount. Every second, you increase by the same amount. Now, if I'm going from 0 to twice the average is going to happen halfway in between. Not only halfway on this axis, but halfway on this axis. In other words, if this whole journey is 3 seconds, that average velocity is going to be the instantaneous velocity right at 1.5 seconds. Right at 1.5 seconds. Now, everyone choose B. This is going to be the one time we're all going to get the right answer. Okay? The instantaneous velocity and the average velocity have the same value, B, somewhere in the upper half of the track. Okay, we're all going to get the right answer here. Whoa. Got some party guys. Okay, well, let's see why. Remember, it takes this cart 3 seconds to get down the ramp. So 1/1000, 2/1000, 3/1000. Where was the cart at 1.5 seconds? 1/1000, 2/1000, 3/1000. Okay? During the first second and a half, it's speeding up from 0 to V average. It's going slow. During the last half of the journey, the last second and a half, it's speeding up from V average to twice V average. It's going fast. On average, it's going 3 times faster during the last half of the journey. And we can show, I'm not going to do it because I don't have time right now, but we can show that the two have the same value. V instantaneous and V average have the same value 1/4 of the way down the ramp. Exactly 1/4 of the way down the ramp. See if your neighbor is convinced that it's in the upper half of the track. Don't worry about the quarter, just the upper half. Okay. Let's continue our discussion of kinematics. A boat is cruising at 3 meters per second. At time t equals 0, the boat begins accelerating with 1.6 meters per second every second. How far will the boat have traveled 10 seconds later? Now the question is, which of these equations do we want to use to solve that problem? Well, we're looking for how far the boat will have traveled. And there's my delta x right there. But the problem is, if I try to use this equation, it demands that I know the slowest speed and the fastest speed. I only know the slowest speed. I don't know the fastest speed. Well, how could I find that final speed? Well, I could use this equation. And so it turns out that this problem requires that we use both. Now, I could use this equation to find V final, and then plug it in here to find the distance. Or I could cram these two equations together in such a way as to make a new equation. If I take, instead of V final, I write V initial plus A delta T, I plug all of this into there, I get a new equation. Okay? So, the first step, let's do it the old way. What is the boat's velocity after 10 seconds? Well, I would use this equation and say V final is equal to 3 meters per second plus 1.6 meters per second every second times 10 seconds. That's going to be 3 meters per second plus 16 meters per second, or 19 meters per second. Then, I find the average velocity. Well, the slowest is going to be 3, the fastest is going to be 19. I add those together and I get 22. Half of 22 is 11. So on average, this boat is going 11 meters every second for 10 seconds. How far does it go? 110 meters. Now, let me show you the way without your brain. So we just did it with our brain, and we got an answer of delta x is equal to 110 meters. What we do is we combine the first two equations in such a way that we eliminate b final, and we get this equation. We can also take these first two equations, solve this one for delta t, plug it in there, and we get this equation. Now, those four equations are known as the kinematic equations. They will be on the front page of your exam. They are on page 21 of your textbook. This chart will not be on the exam, but it's obvious what it is. In kinematics, in motion, there are 5 players, 5 variables. And each one of these equations has 4 of those variables and is missing one. Okay? And that tells you which equation you're going to plug and chug into. Okay? The one that gives you the right variables.